take a look at this flexible OLED prototype. Our team was able to make a high-resolution display on extremely thin plastic, so instead of glass, so it won't break even if it's dropped, and we can actually bend the screen. Imagine the products you could design with this. Imagine the products you could design with this.
Wow, that is super cool. So how is this done? How do they make those? And what's changed? Why now? Why only in this year or this time are we currently getting these electronic displays? Well, I think we best way to investigate. I don't know about you. So a flexible display will need to be thin enough that you can actually flex it. It'll have to be a material that can flex, so it can't be something breakable such as glass. And I suppose it has to be bright enough to actually be a display in the first place. This is a picture of someone who's sitting down watching our TV. Imagine this is our TV. So back in around about 1934, from what I've been reading up, that's when the first commercially available CRT, cathode ray tube television, was available for the public. Would it have been possible to try and bend this display here? Is there some way we could pull our TV screen? You can see that I put an electron gun. Basically, energy would have been fired out the back of this TV and going towards the front. It would hit the screen, and what we're going to focus on is what is going on here. What actually happened at the screen? Why did the screen have to be so thick? Why couldn't it be bendy?
So first of all, let's look at having blue, green and red light together. If you mix them all together, that creates white light. I want us to focus on just in the middle bit, okay? Imagine that the rest of the circles don't exist. We're just going to focus on this middle bit here. Now, what happens if we remove the blue, and the colour will change, and we'll get sort of like a brownish sort of colour, I guess, green and red. And then if we take that away, we'd only get a red. And then also, I want us to imagine if we took away everything, it would end up being black.
Now here, I have drawn it with exaggerating the angles, so that we can understand a bit more what's going on. We will have 3 electron guns. One that will represent the blue colour, one that will represent the red colour, one that will represent the green colour. Now what I want us to not get confused about is to think that actually green light comes from inside the TV, or red light or blue light. It does not come from inside of it, only the energy does. Here I'm going to give a very simple explanation of what phosphor is. There's one type of phosphor, and energy will go into it. Say it's from our TV. Energy will come in. This will then react with the particles that are enclosed in this small space. This will do some chemical reaction. I don't want to go too much into this in this video because I want to focus more on the screens rather than chemical reactions. And out will come this red light. So it's changing energy into photons, if you want to know. Then, of course, we have the same thing. We have a different type of phosphor, which then, of course, creates different reactions. So we have green that comes out from this phosphor, and then we have another type of phosphor with other energy, with other chemicals in it, and then this produces another type. Basically, that's it. 3 different chemical formulas produce 3 different types of light coming in from the same energy, the same energy source, but different colours will come from it. This is basically phosphor. Continuing the story. Energy coming from our blue electron gun, if you look, if it was to follow this angle so it can't fall other places, will end up at this spot here. Unlike, say, energy that came from the red. Remember, this is not colours that is travelling from here, it's only energy. Each of these 3 lines therefore would hit a different part of the screen.
The shadow mask, or aperture grille, is a metallic plate with several holes in, which is used to separate the energy from the 3 different electron guns so the energy can strike the correct piece of phosphor.
This diagram here is showing what's at the end of the shadow mask. What I'm saying is that energy will come into this. This would then excite our phosphor atoms that are inside it, so it's exciting a load of phosphor, and then from that, some light will come out. This we'll come to in a second. And also the idea of the shadow mask is that if other energy came in from another electron gun, it cannot pass it, it will not affect these atoms. Let's not forget one other thing. This is actually an electron gun. The clue is in the name. This is a huge amount of electricity that is being fired, well, basically towards the person's face. So electricity is literally leaving this gun, getting to this point, and then, well, if this screen wasn't here, it would go straight on and could do quite a lot of damage. How much damage are on about? How many volts do you think are in this actual TV? Well, inside everyone's living room, there was actually something towards 20 to 40,000 volts. Trust me, you want to have something very, very strong here to make sure that this does not go into your face. Let's sum it up. CRTs, are they flexible? Well, just looking at the screen, let's not forget the big distance that the energy has to travel in the first place from our electron gun. We'll then get to the shadow mask that we talked about briefly before. Then we'll have where the actual phosphor is stored itself. Then after that we have this big sheet of glass to protect ourselves from all the energy. In fact, this sheet of glass here also contains lead because we want to avoid any sort of harmful radiation that could have come from inside the TV, so that our person can still sit here and watch the TV. So it looks like our old classic CRT TVs couldn't have that bendy screen that we're looking for. But what about plasma or LCD screens? Why weren't they ever bendy? Let's find out.